have you understand the difference between atoms, isotopes, and ions. In our last video, we looked at an atom and realized that the number of protons was equal to the number of electrons, and therefore there was no charge. We also found out that we could figure out the amount of neutrons by subtracting the atomic number, or the number of protons, from the atomic mass. Of all those three particles, the one thing that identifies an atom is the protons. These are three different isotopes for hydrogen. You'll notice that in all three images, there is exactly one proton and one electron. What we see that has the same is one proton or one electron. What's different in all three images is that the first one has 0 neutrons, the second has 1, and the third has 2. What is different is the number of neutrons. What we know about atoms is the one thing that can never ever change is the proton. In the case of an isotope, isotopes are different forms that an atom can take, where the number of neutrons is different. You can substitute the word isotope for form, and it makes more sense. There are 3 forms of hydrogen, or there are 3 isotopes of hydrogen. The difference is the number of neutrons. When we write the isotope name, I write the name with a dash and a number. The number talks about the mass of that particular isotope. So isotope of hydrogen named hydrogen 1 has a mass of 1. Hydrogen 2 has a mass of 2 because there's 1 proton and 1 neutron. And hydrogen 3, with 3 large atoms, or large subatomic particles in the nucleus rather, this would be hydrogen 3. Hydrogen 2 and hydrogen 3 have common names and are called deuterium and tritium. Because most atoms have several isotopes, we can, if we're discussing isotopes, write special symbols to identify the fact that that is what we're interested in. An isotope name is always in this form, where we have the name of the element with a dash and then the mass of that element. We can also do an isotope symbol. An isotope symbol has the symbol for the element, and then on the upper left-hand corner, we put the atomic mass, and on the lower left-hand corner, we put the atomic number. The 4 corners where we write numbers around an atom symbol are very important. They all have distinct meaning to chemists. The upper left corner is always reserved for mass, and the lower left corner is reserved for the atomic number. So isotopes, hydrogen 3 would be written hydrogen with a 3 on the top and a 1 below it. In this example, we have isotope names and their symbols. We can break down the information from there. So for U-235, this is U for uranium. Uranium has a mass, an isotope mass of 235, so I put that mass on the upper left corner. Uranium is at number 92 on the periodic table, so its atomic number is 92. This means that I have 92 protons. To calculate the number of neutrons, I will go and subtract 235 minus 92. This leaves 143 neutrons in uranium-235. The number of electrons will always be the same as the number of protons, 92. This way, we have 92 positives canceling the charge of 92 negatives, and we have an overall neutral charge. Isotopes are still atoms. The approximate atomic mass of this element is 235. Remember, this tells us the mass of the element, and this number tells us the atomic number. In the bottom example, we can see that we're going to have an element that weighs 238. 146 of that came from neutrons. Remember that the number of protons added to the number of neutrons will give us the atomic mass of the element. If my atomic mass is 238 and 146 of this came from protons, then the remaining 92 came from protons. So I also have 92 protons. Remember that the proton defines the atom, and we've already discovered that the element who has an atomic number 92 is uranium. This uranium weighs 238. It weighs somewhat more than the other isotope of uranium because of its extra neutrons. It still has the same amount of electrons as it does protons. The electrons have nothing to do with the mass. The name of this element would be uranium-238. Why then on our periodic table are the atomic masses always written with decimal points? The atomic masses of the elements that you find on the periodic table are the average of all the different isotopes. But the isotopes don't always occur in equal amounts. Consider, for example, boron. Boron, with an atomic mass of 10, accounts for 19.9% of the boron that you'd find in any sample. The remaining 80.1% is boron that weighs 11. So clearly the average mass of boron should be much closer to 11 because there's so many more atoms that would have that mass. In order to calculate the number that we get on the periodic table, I will take the percent abundance for each particular isotope multiplied by the mass of the isotope. So for example, I have 19.9% of boron weighing exactly 10.013 atomic mass units. Changing that percentage to a decimal, 0.199 times 10.013 would be the abundance of the isotope times its mass. To change a decimal point, a percentage to a decimal point, 19.9, there are two ways you can look at it. You can go divided by 100 on your calculator, or you can simply move your decimal point back 2 spots. Either way, you have now changed your percentage to a decimal point. So here's the percent abundance for boron 10 and the actual mass for boron 10. For boron 11, the percent abundance is 80.1% or 0.801, and the actual atomic mass is 11.009. Doing the math, the product of my isotope for boron 11 and for boron 10 are added together, and I get that we will find an average atomic mass of 10.811, which is the number you see on the periodic table. I'll do one more example with you. Let's calculate the atomic mass that we would get for silicon. Silicon comes in 3 different isotopes. We can have silicon 28, we can have silicon 29, and we can have silicon 30. Silicon 28 is 92% abundant. 92.23% is the same as saying 0.9223. We're going to multiply that by the actual atomic mass, which is 27.9769. For silicon who weighs 29, we notice that it is only 4.67% abundant. So 0.0467 multiplied by its measured atomic mass, 28.9765. And for silicon 30, which we find only 3.1% abundant, multiplied its measured mass of 29.9738. We can do the math quickly using a calculator and then take and add the total of these 3 values together. Once our math is complete, we come to an average atomic mass for silicon of 28.0855, which is the atomic mass that you find on the periodic table. As a quick recap, the rules for solving average atomic mass are to first change your percent sign to a decimal. Then multiply each decimal that you got by the corresponding atomic mass, and then add up all of the answers from step 2 to get the average atomic mass. Try these 4 questions comparing the answers that you get to the values on your periodic table to practice solving for the average atomic mass of all the various isotopes. So isotopes occur when an atom has a different amount of neutrons from another one of its forms. The protons, however, remain the same. Ions happen when atoms get a charge. Since we can't change the number of protons, the only thing that can be changing when we form is the number of electrons. When electrons are lost, atoms become positively charged. We call these cations. When electrons are gained, atoms become negatively charged. We call these anions. Cations have positive charge, anions have negative charge. In both cases, this happens so that the atom becomes more stable. Atoms gain or lose electrons so that the outermost shell appears to be full. In the case of lithium, with 1 valence electron in the outermost shell, there was 2 choices. We either could have found 7 electrons and transported them in, or lost 1. And since it takes energy to move an electron, it's easier to just lose 1 thing than it is to move 7 things. Once that electron is gone, the outer ring is gone, and the next ring in was full. Lithium's only got 2 rings, and the first ring is full with 2 electrons. Lithium is isoelectric, or has the same electron configuration now as helium. It looks like a noble gas. In the case of chlorine being in group 7 on the periodic table, had 7 valence electrons in its outer shell. Chlorine had to choose either lose all 7 of these or gain 1. And so 1 extra electron is going to come in, and now we're going to have a total of 8 in the outer shell. Chlorine still has 17 protons in its nucleus, but now with 18 electrons, we have more negatives than positive by 1, and chloride as an ion has a -1 charge. Again, this is now looking like a noble gas. Chlorine has the same electron configuration as argon and is therefore more stable. Atoms take the easiest path to form ions. Our metals from groups 1 to 3 will tend to lose electrons. Atoms found in groups 1, 2, and 3 on the periodic table, group 1, group 2, and group 3, have 1, 2, and 3 valence electrons respectively. It is easier to lose them, so any atom found in group 1 will lose 1 valence electron and get a charge of +1. In group 2, they have 2 to lose and get +2, and in group 3, they'll lose 3 and get +3. Elements found in group 4 on the periodic table have 4 electrons in the valence shell. It is equally easy to gain 4 electrons as it is to lose 4 electrons. So sometimes they'll have a +4 charge if they've lost electrons, and sometimes a -4 charge if they've gained them. Atoms that exist in families 5, 6, and 7 are very close to having completed outer shells. In group 5, they will gain 3 electrons to have a full outer shell and have a charge of -3. Group 6 gains 2, and atoms in group 7 gain 1. The noble gases already have complete outer shells and do not gain and lose electrons. Noble gases always have a charge of 0. They do not form ions. The transition metals are actually capable of forming more than 1 ion. And we'll discuss how and why that is in grade 12. There are different areas of chemistry where we use different words to say the same thing. The charge that we're talking about when an atom gains or loses electrons is sometimes called oxidation number and is sometimes called combining capacity. We also know that valence means the number of electrons in the outer shell and corresponds with the group number of the atom where the atom is found. So we now know that atoms are elements. On the smallest form, an element can be found on the periodic table. In an atom, the number of protons is equal to the number of electrons. And we calculate the neutrons by subtracting the atomic number from the atomic mass. Isotopes are the different forms that atoms take when they have different amounts of neutrons. Ions are the different forms that atoms can take when electrons are gained or lost in order to become more stable and have an outer shell that looks like that of a noble gas. To help you practice these terms and understand these, there are questions in your textbook on page 129 and also page 209. Also, on page 12 of your workbook, there is a worksheet that helps you to reinforce the terms that I said had similar meanings on the previous page. Once you're done with this lesson, I'm hoping that you are able to define and give examples of isotopes and calculate their average atomic mass. I hope you can explain what ions are and how they are formed and differentiate between cations and anions.